so we're going to start with this one, the hanging box. And look at it. Of course, folks, remember you don't have to follow along, but you at least have to be quiet enough that I can hear myself. All right, so try that out. So in this one, we're looking at the forces on this box. If I can blow this up just slightly. There we go. Alrighty, so let me grab this diagram. I don't feel like redrawing. Alright. We have hanging box. So, let's see. We need to do our forces. I'm going to kind of ignore this little rope here because I'm just going to look at as if these two lines were connected to the box here. So, of course, the box has some weight down, and then I'm going to say it has a force. I'm going to call that force R for right-hand force, and then a left-hand force that goes up like that. Maybe I should do a components of my left-hand force. So if my left-hand force points in that direction, if I wanted to do components, a horizontal and a vertical component, this angle here would be theta, because if you look at the geometry, it's just opposite what theta was. So this side would be FL cosine theta, and this side would be FL sine theta. And so I can use those green forces actually to replace the FL force, which goes in 2 dimensions. So my approach to all of these equilibrium type problems is virtually the same. In fact, my approach to most of these is identical. I'm going to start off looking in the y direction, and the sum of the forces in the y direction equals 0. All right. And in the y direction, I have 2 forces. I have my weight, the weight of the box, and also the vertical part of my left-hand force. Remember, I'm replacing that left-hand force with the 2 components. So I'm going to call up positive, so that'll give me FL sine theta minus F sub g equals 0. And I can go, oh, that FL sine theta then equals F sub g, which I remember from my equation sheet is also equal to the mass times the gravitational field, mg. Because that's the weight of the object. And if I want to get that left-hand force, I could rearrange this and get that the left-hand force equals mg over sine of whatever my angle is. And then I could substitute in my values and have my left-hand force, right? And then that gives me my left-hand force. Now I need my right-hand force. So I'm going to say, okay, what if I looked at what's going on horizontally here? Sum of the forces in the x equals 0. Horizontally, I've got the right-hand force, or the right-hand tension, however you want to think about it. And I've got the component of the left-hand force that's horizontal. I'm going to call it to the right positive. So that gives me FR minus FL cosine theta, and that equals 0. So FR equals FL cosine theta. And I know FL because I found it in the previous part. And I know theta because they told me that. So there's my right-hand force. Most of these problems are going to be do the force diagram. Use that to organize your forces into vertical and horizontal and solve. They all kind of follow the same type of pattern, hence why we did them as one big group. So give it a try. I'll start another problem in just a minute. All right, so we're going to move on to doing rock across the ice, which was another one that was asked for. And in this one, we've got a student pushing a rock across a frozen lake. And you're given the coefficient of friction between the rock and the lake. And you're also told here on the side, the push with the downwards angle of this, and what force does the student need to push to keep the rock moving at a constant speed. And then another time they pull it, and again you have that constant speed. When you see things like constant speed, the first question you should ask yourself is it in circular motion? If it is, then you have an acceleration towards the center to keep changing the direction. If it's not, like this one isn't, then right away that should key to you, oh, they are trying to say there's no acceleration, and they're just saying it in a different way. Or the other way to think about that is there's no total or net force. So the best for this would be a free body diagram, a force diagram again. You could show that little bit of that understanding that, hey, I know there's no acceleration, but I'm going to do that in my diagram. So here is the student pushing it, and here is the student pulling it. In both cases, there's going to be the weight of the rock down. There's going to be a normal force from the surface back up on the rock. Since it's moving to the right, in both cases, there's going to be a frictional force to the left. And the big difference is that on this, when they're pulling, the force that they're pulling with F is going to go up. And when they're pushing, that same force F is going to go down. Or a different force F. Let's call this F1 and this one F2, just so we don't mess them up. All right? And as I did before when I had forces in more than one dimension, I think it would be good to do little component diagrams of them. See, they say the angle is up there and down there. So I'm going to draw components in these directions, where my angle is 24.5 degrees. So this angle here is 24.5 in both cases. This is F2. This is F1. So I can write here F1 cosine 24.5 degrees since it's adjacent. And across, I'll get F1 sine of 24.5 degrees. Here I get F2 cosine 24.5 degrees. And here I get F2 sine 24.5 degrees. Very similar, if you notice. What's the big difference between those forces, though? Right, the direction of the vertical components. In F1, it's pointing downwards. In F2, it's pointing upwards. So that's the big difference in contribution. Let's look at part A first, where we're pushing down on the rock. they want us to finally come out with the amount of force they need. So I'm going to remember a couple of equations, things like that the weight of the object is mg, that frictional force equals mu force normal. All right, so I'm going to keep those type things in mind. And well, let's do the vertical force first. So in the y direction in that first diagram, sum of the forces in the y equals 0. And remember, I'm using the components, the green components here, rather than F1, because I want to be able to work in X and Y rather than having to do them together. So in the Y direction, in that first situation, I actually have three forces. I've got the weight, the normal force, and the component of the force that they're pushing with. So I'm going to have, let's see, we'll take up as positive, so force normal minus the weight minus F1 sine of 24.5 degrees equals 0. So I'll pull those three out of my diagrams. And I can't go very far, but at least maybe it'll help me later to write that the force normal equals the weight plus the component of the force that the student is pushing with, right? And of course, rather than F sub g, I can put in there mg using my identities from that I know from up top. And then, well, I didn't get to an answer for F1 in that step, so maybe try it the horizontal forces. In the horizontal direction or X direction, I have friction and I have the component of the F1 that points horizontally. So I'm going to start the same way. Hopefully you're starting to see a pattern of these starting parts. And we'll call to the right positive. So I have F1 cosine 24.5 degrees minus the frictional force equals 0. And so I can write that F1 cosine 24.5 degrees equals the frictional force. Using my identities from up top, I can write mu force normal rather than the frictional force, right? And, oh, maybe substituting in, I can start to get rid of some of these things I don't want to have to really deal with. So let's bring those two equations together and be able to write F1 cosine 24.5 degrees equals mu, coefficient of friction, remember, times mg plus F1 sine of 24.5 degrees. Well, that's good because I know, let's see, I know what mu is. I think they told me in the problem. They did, 0.39. I know what the mass of the rock is, 53 in my case. I know what planet we're on, so I know the gravitational field strength, little g. In this case, it's 9.81 newtons per kilogram. So the only thing I don't know in this red equation is F1, which is what it asked me to solve for. So that's kind of neat. So all I need to do is rearrange this to get F1 by itself. So something like F1, probably, expand out this. Using my good old algebra rules. and then factor F1 out. I'd be left with and I know everything still except F1, so I can solve for F1. Yep. Huh? Okay. I'm going to keep going if that's okay. So in part B, they now have the person pulling the rock, and one of the big differences will be in the y direction, but I start exactly the same way, except if we go back up and look at our forces, now we have the component of F2 pointing upwards rather than down. So in my equation, it's going to go in as a positive number. Still have my normal force and my weight. So I can substitute in here that my normal force minus the weight, but now I've got to add to that F2 sine of my 24.5 degrees, and that equals 0. So I end up with a normal force that is Fg minus F2 sine of 24.5 degrees. So what it's effectively done is reduced my normal force. What if I reduce the normal force, what's that going to do to the friction? Decrease it also. Right. So it's going to decrease it. So if I have less friction, then it's going to take me less force to overcome that friction. So I'm hoping I get an answer that's less for the second part than the first part. So now I go into my x direction, do the exact same thing. All my forces are really in the same direction as they were before. So I have F2 cosine of 24.5 degrees minus the frictional force equals 0. Getting those from my diagrams. And so I can again say, well, F2 cosine of 24.5 degrees equals the frictional force, which is mu force normal. And really go through a very similar substitution as I did before. F2 cosine 24.5 degrees equals mu times Fg. Let's write mg there, right? Mg minus F2 sine of 24.5 degrees. And I can do a lot very similar algebra to what I did in the first part and solve for F2. All right? So very similar except for, notice it's the weight minus the component of the force here, and in this uppercase, where we were at that point, it was mg, the weight plus the force, that component. So the only thing it changes is that it affects the normal force, which reduces the friction. All right, we only have a few minutes left, so I think I'll jump on this one because it's a little bit different than the other ones that you've asked for today. This is about circular motion. And this actually goes right back to what we ended yesterday with. Remember the video of the car going around? So you've got car here going around a corner of this radius at this speed with this coefficient of friction. Assume the car doesn't skid. What is the force exerted on it by static friction? So, so this is 9.81. I'm going to do a free body force diagram. We'll say that the car is right here. There's the center of the circle. and it's going around the circle, so it's actually coming towards me, so I'll draw my velocity vector that way. Since its weight would be down, the normal force would be up. It's going to have a frictional force towards the center, because since it's in circular motion, it has to be accelerating towards the center. So it needs a force that points towards the center to create that acceleration. And in this case, it's a frictional force that does that. Just like that, what we saw in the video, short little video clip yesterday. So I can come over here and I can do some of the forces in the x equals max. I have to include, it's not 0 because it is accelerating in the x direction. I'm going to call towards the center of the circle of that dot I drew positive. So I have frictional force, my only force, mass, and then my acceleration is a centripetal acceleration. Because remember, centripetal acceleration only changes the direction, not the size or the magnitude of the velocity. So that's, and it points towards the center circle, and that's why this one is centripetal. From my equation sheet, I should remember that A sub c is v squared over r. And it actually wants to know that frictional force. So really, this is just m, which I'm given, v squared. I'm given v over r, the radius of the corner that it's taking, or the radius of the circle. And I'm given that also. So I have m, I have v, I have r. I should be able to combine them and find the frictional force. All right. I'm going to save